Looking forward to this conversation today. So just to set some expectations here, I'm going to have a conversation with Mark for a bit, and then we're going to segue into a panel session that also deals with NTN. So Mark Dankberg, CEO and Chairman of Viasat, and also heads up the newly formed MSSA, the Mobile Satellite Spectrum Association Alliance.
Mobile Satellite Services.
Services. I'm still working on some of the satellite-related acronyms coming at this from telecom. It's as new to me as it is to some of the other people in the industry. All right, so I think I'd like to start with some of the, and I'm Kelly Hill. I'm executive editor of RCR Wireless News. We're a trade publication. I've been covering this space since about 2.5G. So it's nice to see the evolution, as always, and what gets kicked down the road. But we've got some interesting things happening in standardization, particularly when it comes to NTN. We're seeing a lot of developments that I think sort of encompass this intersection of cellular and non-terrestrial networks. That includes high-altitude platforms, as well as LEO, MEO, GEO, and satellite. So we're seeing services starting to be tested. You're starting to hear things from T-Mobile, from AT&T, from Verizon. We've got carriers making deals and partnerships. We've got satellites going up. AST Space Mobile just recently got their first 5 Bluebirds up and ready to start beta services. And so we also have device OEMs getting into the game. I'm thinking particularly of Apple and Google on the newest Pixel. They are incorporating emergency satellite service capabilities that are just included with the device for the first 2 years. So all of those things are happening now. So what makes this sort of the conversation of the moment across the industry? You know, why is this feasible and happening right now?
Okay. Yeah, I think the thing that is really the catalyst for all this is that the chip companies have realized that they can integrate satellite capability into the phones with essentially no, very, very marginal additional cost. So that means really supporting physical layers from the satellite on the modem chips, and then making the front end support those frequencies. So that's an exciting invitation to satellite players, because now you've got the potential of having billions of users on the network, as opposed to, say, millions, which is kind of what the market is for now. So and then what that's driving is that satellite operators are looking and saying, okay, what does it take for me to physically close these links? And then also, what kind of services can I deliver? And just from a link analysis, physics perspective, it's exciting. There's exciting opportunities. The one thing I would add also to what you just said, which really relates to both what Apple and Google are doing, is you can enhance these services with new satellites, but you can already offer them with the satellites that are in space. So Apple's working with a Globalstar low Earth orbit constellation, and Google is doing their emergency services with our constellation of GEO satellites. But there's, it's going to be in phases. So first, I think one of the other big enabling things, which took advantage of what was going into simultaneous with the modem chips, was the 3GPP NB narrowband IoT standard, Release 17, which is the low data rates, texting, messaging type of services, which is going to be followed by the new radio spec, and that's the one that will really benefit from the new satellites that are going up.
Okay. So you mentioned the physics of this. And then there's also obviously the business case question. So I'm going to ask what you see as the limitations of non-terrestrial network technology, either technically or in terms of the business case.
Okay, so think of it, and this goes a little bit to the Mobile Satellite Services Association. There's already an ecosystem of direct, to user satellite services. There's Iridium, Globalstar. We have sat phones. There are a number of different sat phones out there. Also, you can see satellite services embedded in devices for hikers or others, right? So that ecosystem has existed. What the big thing now, that's the attraction, is instead of having a special device, every device is enabled. The big issue is the antennas on those terrestrially centric devices are very poor compared to these satellite-specific devices. So the first limitation is overcoming those poor antennas. And I say it that way, but on the flip side, I'm sure everybody in the satellite industry is thinking, yeah, that's a worthwhile challenge to overcome, okay? But that's one. And the other one is there are a number of other complications. One is, okay, well, you know, how do you get more advanced services through those? And that's really going to involve more power from the satellites, greater power flux density on the ground, and that's creating the potential of interference with either terrestrial systems or defense systems. The bands that are likely to be used, which I think are mostly in the 1 and 2 gigahertz range, those are very congested bands. There's potential for interference to terrestrial cellular networks, other satellite networks. So one challenge is to overcome those while also delivering the power you need to deliver the services you'd like. The other one is, another really interesting challenge is figuring out what those services will be. So, and I think, you know, what's happened often with satellite, not just often, pretty much every time with satellite, is people envision satellite services for rural areas like satellite TV, but it turns out the absolute number of people who benefit from satellite services in metro areas or in the populous states tends to way overwhelm the number of people that would use them in rural areas. And that's, the penetration is clearly much higher in rural areas, but the sheer number of people in metro areas means the absolute demand tends to be clustered in the more populous states. So you'd find way more satellite users of satellite internet or satellite TV in New York than you would in Montana, as an example. So, so one of the other big challenges is how do you make services that have sufficient, you know, bandwidth density, that you have enough bandwidth available to serve the demand in these high demand places, which is that becomes a challenge when you have a cell tower that is hundreds or thousands of miles away. Then that becomes a challenge to make coverage areas, satellite, they call them beams, but they're basically cells. Those are some of the challenges. The other one, which we see is a really interesting opportunity, is, as I mentioned before, there are millions of people around the world that use these mobile satellite services now. A lot of them, especially our customers, tend to be aeronautical safety customers, maritime safety customers. So those are really important missions. There's an opportunity when you bring these non-terrestrial network technologies to market, where they can get better services, better value, lower cost equipment, more pervasive, not even need special equipment. But on the other hand, you want to make sure that you bring them along and don't disenfranchise them. So that's a really interesting challenge as well. And then finally, the other one, that is, I think, a really, really important challenge is the national security implications of this, which we heard a little bit last time. But the big difference between satellite services and terrestrial services in a country are that with a satellite service, you can bypass the entire national telecom infrastructure. And that is a scary prospect for a lot of countries. And you can see that, you know, with some satellite operators saying, hey, if we don't like these laws, we may not comply with them just because we don't like them. And if everybody in your country with a cell phone has the ability to bypass your entire terrestrial infrastructure, that's a scary prospect, right? So I think that dealing with that, even if it's, you know, even if you're not necessarily concerned about cybersecurity leaks, it's just if at the whim of a foreign operator, they can decide that they don't want to comply. that's another layer of complexity.
On both sides, in terms of, there are consumer protections, GDPR, regulatory regimes that, in some countries, are very specific about consumer protections. In others, there's a lot of surveillance, and there is, we want to be able to see where everybody is at all times.
Yep. But it's hard for international players to take a posture that doesn't comply with national laws. And those can be delicate balances, but especially in things that involve like aeronautical safety or maritime safety, there's motivations for countries to cooperate. And just in terms of flyover rights, things can be unbalanced by times of war, but in general, I'm just going to give an example. I mean, Western countries want to be able to fly over Russia to get to Asia. Otherwise, you add hours to a flight time. There's examples like that sort of call for some levels of international cooperation. And I think my main point is that all these problems are understood and can be overcome. Some of them involve network policies, ways to engage countries to participate in these networks. If you are aware of these problems, you can design networks in ways that countries can maintain the sovereignty of their network and still get the benefits of NTN. Customers can still get roaming agreements. In some ways, example, one of the things we do is we do in-flight communications. We have partnerships where, for instance, where somebody could take a flight from the US to China, could have coverage all the way. I mean, Americans still go to China, or some go to countries where telecom might be challenging, but still can get certain connectivity or internet access. So those things are all achievable.
So this is a 6G focused event. As someone who comes to this from the cellular side of technology, what do you think about that the terrestrial, cellular, and network folks in the room really sort of need to understand about satellite technologies?
Well, so one is what we're aiming to do, and this is one of the things about this Mobile Satellite Services Association, is that what we believe is that the 3GPP standards that are being designed into non-terrestrial networks they're workable, that we can support them over satellite. Another one is that we can do it in ways that haven't been done before with the satellite services. So we can come up, like open architecture, a big theme last time, where we believe that we can create open architectures which allow technology insertion, but also really importantly, roaming among different spectrum holders. So one of the things you'll find now is in the mobile satellite services world, there are quite a large number of different satellite operators. A handful are global, a lot of them are regional, some are national. And one of the things that we're looking to do is to create essentially infrastructure in space, which is open and can be shared by multiple satellite service providers. And that will give terrestrial operators a lot more choice in being able, if you think of satellite service as augmenting their terrestrial service, either within a country or internationally for roaming, we can create a roaming environment where just as if when you're roaming to a different country, you have the opportunity to roam through space to multiple different spectrum holders and service providers. So those are some of the open architecture benefits that we can do. We can also deal with things of like network infrastructure gateways in local countries that can give a carrier more assurance that that carrier's customers will be able to get service when they roam into different countries. I think that different satellite service providers may have different approaches, technical approaches, whether, for instance, do they land traffic in a country, which would be much more friendly to that country being able to enforce its own national and sovereign laws, versus others that might only land traffic that originates in that country in a foreign country, which would then be more of a concern from the cybersecurity perspective. So I think the big thing is many of the same principles are going to apply. I think there will be relatively modest modifications to the O-RAN infrastructure, but I think that these issues of cybersecurity, and how you manage beams and cells from space are going to be big things for terrestrial networks to pay attention to. I'll just give you one more example. Like one thing that people are doing is they're extending this notion of emergency services from the rural areas into, hey, well, maybe I can do the same thing in a metro area in the event of a natural disaster. But think of it, the demand, the number of people that will want emergency service in a metro area in a natural disaster is many orders of magnitude greater. And basically, it's just going to be like terrestrials. If you want density of service, you're going to need lots of spectrum. And so that's where being able to aggregate the spectrum from all these different mobile satellite services providers, where you can get the potential of hundreds of megahertz of spectrum available as opposed to just single-digit megahertz. It's going to make a very big difference in your ability to serve these important emergency services in metro areas. That'd be another thing to think about.
Okay. So I think on the regulatory side, I want to get into that a little bit because we've seen the FCC create the Space Bureau, create a path for supplemental coverage from space, and then we're also seeing some things play out right now between some of the carriers in terms of power level discussions and NTN very directly. So what do you think are the regulatory issues of primary importance right now for NTN?
Well, I think clearly there are a few satellite operators that are promoting the supplemental coverage version, which is, hey, you can take some of your terrestrial spectrum, allocate that, and now you have something you as a carrier control. And I think that those proceedings will go on. I think that that's a way to get spectrum. It's a way for a carrier to have control. I think the big issue from a carrier's perspective is because of the distance, even from low Earth orbit of hundreds of miles, the yield, the economic utility of that spectrum when used from space will be much lower than if it was used from terrestrial. So, and then the other issues are going to be especially crossing borders or territories. Those are some of the issues that are well understood. I think there will be another way, which is using these licensed mobile satellite services spectrum that already exist. They're already coordinated. There's mechanisms to coordinate among each other and among terrestrial uses and the other sort of defense uses or government uses that were described last time. So that's another path. There's a lot more spectrum there. And one of the things, rather than thinking about it as an exclusive service of a particular carrier, you can think of, as we build out this open architecture system with 3GPP standards, it just creates a lot of different roaming partners, maybe on a global basis. In a single country, there may be just 2 or 3 or 4 like there would be for roaming partners for terrestrially, but now one of the business models is just non-exclusive roaming agreements bidirectionally, where any of these carriers that support the standards could support either the narrowband or wideband functions or services, and then any operator could dynamically choose, just like they do with roaming from any of the satellite licensed satellite spectrum holders. I think that we'll see both of those tracks come to market, and then it'll create more options for the terrestrial cellular operators.
Okay. So Viasat was one of and you mentioned MSSA.
Yeah.
So Viasat was one of the founding members. You're heading that up. This includes quite a few companies that have MSS spectrum. You also had Ericsson join as a member recently, which was interesting. So what do you hope that MSSA can accomplish?
So what MSSA is really trying to do is create this open architecture framework. And that is new. If you look at what has happened in mobile satellite services in the past, each licensee has generally had their own network and system. So an Iridium device wouldn't work on a Globalstar network or an Inmarsat network or Viasat. The network standards were different. So here, given the standards and the open architecture, there's an opportunity for interoperability. And what that should do also is make the economics of implementing those services much more cost effective. So that rather than having to have a satellite, Iridium has its own satellites, Globalstar has its own satellite, we have our own satellites, you can have satellites that can support all the spectrum, and they can support a common set of networking standards. So that should reduce the capital investment, which should reduce airtime costs. What we think is one of the things that's going to drive interest in these non-terrestrial networks is getting those airtime costs to be much closer to terrestrial airtime costs. Where right now you're talking about dollars per megabyte, typically, for mobile satellite services. Terrestrial services are dollars per gigabyte, so that's 3 orders of magnitude. But I think that can be overcome using these open architectures, more powerful satellites with the 5G new radio capability, and especially one of the main ingredients is aggregating spectrum, because network capacity grows linearly with spectrum, but only with a log of power. So there's a really, just like in terrestrial, really big advantage to having aggregated spectrum. I think that's what's going to tilt a lot of interest towards using these mobile satellite services, is that the airtime costs will be lower, and you won't need to raise airtime prices to manage the demand, which you otherwise would in a market. If the services are inexpensive, but you only have a small amount of spectrum to serve them, then even if they're priced below cost, there's not the network capacity to serve them.
Yeah, okay. We've got a couple minutes here. Any questions from the audience? Yes, Roger.
Sorry, I can't resist. The aggregated spectrum thing, let me poke on that a little bit. I don't know an operator in the terrestrial space that likes to share spectrum, period. And it's just because you can't control the customer experience. What you're suggesting is that the satellite operators, right, service operators would actually share, right? Expand on that a little bit more. How contentious are those discussions in the NSSA?
Actually, they're not contentious. The main reason why is this issue about elasticity of demand, right? I think that it's really important in order for there to be sufficient demand to drive airtime costs down. I'm just going to give you an example. Like if you look at, let's say somebody could do an emergency service, with a Pixel or Apple phone, and let's say that message, which is very short, costs you pennies or $1. Let's say $1. But if you tried to send a JPEG picture along with it, that might cost you $100, right? People aren't going to do that. So the key to lowering those costs is really aggregating spectrum. So there is a game theory element to it among the operators, which is if we cooperate and bring more spectrum to market, that will drive up demand. That's what we think is what's going to drive up demand. The other things that are important are a lot of these mobile satellite spectrum holders are regional. There's only a few that are global. Mobile network operators want global coverage. So there's about 3 of us that have global spectrum, but a lot of the others have regional, and that's less valuable. But when combined with global, that makes their spectrum more valuable. From the perspective of a global spectrum holder, having that depth of spectrum makes our services more valuable as well. So those are some reasons to cooperate. I think those are clear to a lot of the existing operators. The other really big thing is if you look at the economics of putting a whole constellation into play for only a few megahertz of spectrum, that's not super attractive, especially in an environment where you want to drive down airtime costs. So making the satellite infrastructure support multiple different spectrum holders is a good thing. What I think we're all counting on is that the demand will go way up if the pricing is reasonable. If people look at this as an economical way to augment terrestrial coverage, we think there's a lot of demand, and that's probably the best bet.
All right, so I'm going to call the rest of our panelists up. If you could join us up here, and we'll broaden the discussion. Great. And if each of you could just take a moment to introduce yourselves and let folks get a sense of where your perspective is coming from today.
me start?
Go ahead, Carmel.
Sorry. Hi, I'm Carmel Ortiz. I'm the SVP for Technology and Innovation at Intelsat. We're a global satellite operator. And what my team is primarily focused on is looking at sort of Horizon 2, Horizon 3 technologies and technology development that we bring into the network for the benefit of our customers.
Hi everyone, I'm Josep Jornet. I'm a professor at Northeastern University and also the Associate Director for the Institute for the Wireless Internet of Things. Some of you might remember, I usually only talk about high frequencies, sub-terahertz and terahertz. And yes, today I'm trying to bring that into the discussion on non-terrestrial networks.
I'm Mahmoud Kafagi. I'm the VP of Product at Link. And at Link, we're building cell towers in space. We're providing direct-to-device services to our MNO partners across the globe. So my team and myself work closely with mobile network operators to bring that service to the marketplace, to end users, mobile subscribers.
Okay, great. So I think Mark and I have set, I think, a lot of the context that this discussion is happening within. And I think it's also important to sort of note that terrestrial mobile network operators have used satellite for a very long time, but it's typically been in a backhaul to remote sites, backhaul during disaster recovery. And it's been in that sort of supplement to the regular network. With direct device connectivity now possible, how does that change the role of satellite connectivity in the network? And what does that sort of mean for integrating these two networks with each other? Babu, why don't you go ahead and start?
Yeah, absolutely, yeah. So mobile network operators have built terrestrial cell towers for a very, very long time. And the problem is when these cell towers become uneconomic or just impossible to build, like in the middle of the ocean or on top of a mountain, things like that. So that's where direct-to-device would come in, where you'd provide coverage in rural and remote places where the business case of building a cell tower just doesn't work, and this is where it makes sense to provide that coverage from space. So certainly the mobile network operators are looking forward to these types of services to expand their network coverage beyond existing terrestrial coverage.
I mean, I would say that in addition to that, there are situations in which you do have the infrastructure, but this is compromised. So that could also come in handy, and also in regions where there might be infrastructure, but for example, the US doesn't have access to it, or things like that.
Mark?
Yeah, and one thing I would say is we do both, right? So we have direct to device and we also do backhaul. And so think of it as a continuum. If you have, there are many countries that have large amounts of unconnected people. So if you have a village with hundreds or 1,000 people, it's not unusual to find even small towns with low thousands of people have no cellular coverage. Putting in a broadband connection, and then what you'd like to do is use terrestrial cellular to distribute it among the people there. So you'll see that continue even with direct-to-device, because the airtime costs that are delivered at the end, when you have gigahertz of spectrum, the airtime costs are going to be a lot lower than when you have megahertz of spectrum. So that model will continue, but the direct-to-device thing will allow you to get to places where there's single-digit numbers of people or 20 people, where those people could now connect directly to satellite, where it doesn't even make sense to put in this backhaul. So I think you'll see that those things coexist, with one of the opportunities being that a customer, whether they live in those rural areas or just travel through them, with a terrestrial device and a SIM card, or the equivalent of a SIM card, can connect directly to the satellite through the backhaul or through a terrestrial cellular. I think that's what we're aiming for.
Yeah, and I think that's a really important point, is this kind of seamless integration between terrestrial and non-terrestrial networks, right? So whether it's to kind of to let satellite operators close the gap where there's no terrestrial network present, or sometimes just to expand the capacity density, right? So where you get sort of congestion, now you can have devices that can sort of look and say, hey, is it terrestrial or is it non-terrestrial? Now I have choice in the network selection, and it essentially augments the global network.
Okay. So we are starting to see some of these become real. We're seeing, some of the emergency text message services, the NB-IoT-based services start to emerge. AST Space Mobile, which I already mentioned. So does that mean that the networks are ready? That we're pretty much already there. What still has to happen? And can any of you give us insights into that process of service rollout and what that might look like? And Carmel, can I start with you?
Sure, absolutely. So Intelsat, so we have an ecosystem of KU band satellites. So our approach is really a kind of a global broadband approach. So we think about things like a lot of mobility use cases, again, where you're maybe on terrestrial at some point, and then you can roam into a satellite network. We just announced last week a collaboration, a partnership with a top-tier MNO, SoftBank, where we're going to really kind of demonstrate in a phased approach how to make this a reality. So initially using our existing non-3GPP networks and allow sort of roaming and switching between the terrestrial and the non-terrestrial network. Over time and eventually within a couple of years, we plan to have, be running 5G NR natively over our satellites, and so the device will be much more of a seamless switching using native 3GPP technologies. So it's actually here. I think there's a lot we can do today to sort of demonstrate this integration in a much tighter way. I mean, historically, the satellite industry is, we're a bit exotic, right? So small ecosystem of suppliers. We have our own standards, if we can even call them standards. And that doesn't help, the economics. And I think a lot of what Mark was talking about previously is, now we can, with the 3GPP standards and NTN, we can hope to leverage some of the larger ecosystem of what's happening in the wireless world and use much more household name suppliers to build our network and get some economies of scale. So that'll help drive costs down. But it's really, I think it's here today in a kind of, we'll have to do some adaptation on the satellite side, but moving forward, eventually this will be native, TN, NTN integration.
Okay. Let me go to Mahmoud first, because I want to hear about Link's approach a little bit.
Yeah, so our approach is we're backward compatible with all existing phones, right? Like any phones in our pockets now can connect directly to our satellites without any modifications. No software, no hardware modifications. So we are already in commercial service in 8 countries with 9 mobile network operators. And we've been in commercial service for quite some time. And we have agreements with more than 40 mobile network operators that really want to start rolling this service out to their subscribers. The key here is what you have when, right? So right now we have 5 satellites in orbit, and we're increasing our satellite fleet or our constellation as we speak. And there are different inflection points that get you different applications down the road, right? So right now we're starting with messaging services, things like cellular broadcast for emergency services and rural messaging and IoT, because IoT, you can program IoT devices to send message whenever the satellite is overhead. And really, like, providing messaging services to very rural areas. So a lot of the Pacific Islands have gone with that approach to cover islands that never ever had any connectivity before. So even with only a few overpasses a day, there's actually a lot of people who use that on a regular basis. And as we increase the number of satellites, that's when you get to other more robust messaging services, what we generally call seamless messaging. So pretty much looks like the messaging experience you have right now on the terrestrial network. And then as we grow the constellation more, that's when you get to voice data and messaging, and they will be akin to your terrestrial coverage. So yeah, I think it's just a matter of building and launching more of these.
Okay. Mark, it sounds like, a service, if we do see roaming emerge as sort of the primary mechanism for this, there's work to do on the service provider side, obviously, and back-end integration and whatnot, but it's not necessarily something that consumers see. So, integration, your thoughts?
Yeah. Okay, so there's few different things. One is this SCS type approach that you described. That has the benefit of using existing spectrum, so the phones are already capable of it. So that's one plan, is that you can address phones right away. Ultimately, I think there's the issue of how much spectrum will be allocated to that, and if it's done, if you're taking a carrier spectrum, that carrier is likely to do that on a more proprietary basis. The flip side would be using, say, the mobile satellite, the licensed spectrum, take this roaming approach, Now, when you ask about what's here now, Globalstar, the Globalstar satellites are essentially bent pipe transparent satellites. So they can, and actually I think what they're running is an Apple network, which may or may not be the standard, but Apple supports it, right? But Apple is able to do that over those transparent satellites. For the Google Pixel, they're running them over, say, our transparent satellites. We're working with a company called Skylo, which has built a RAN infrastructure that can be played over any transparent satellite. So, but that requires the Release 17 3GPP chipset, which will probably start at the high end and work their way down. But that approach supports the roaming approach. So we can support multiple different devices, multiple different carriers. And I think you'll see both of those things play out. One of the things that is going to be, I think is going to be a factor is if you look at, again, the difficulty of connecting a mobile device to a satellite in space, it's not as seamless as you could leave it in your pocket. You may have to point it carefully, wave it around a little bit. And so there may be operating system things that you'd like to do that maybe, while the phone might work with it, it may not have the user interface things that you'd like. Like, for instance, one of the things Apple did is that they put a little satellite symbol up there to let you know that you don't have terrestrial coverage. So now you might be aware that in order to get this emergency service, I have to do something different, as an example. So what we think is, over time, you're going to see some convergence among these things. Some will require Android-type operating system upgrades. Some will require new chips. I think it's going to take a few years for all these things to converge.
Okay. I'm going to talk about spectrum. So I think that there's been a lot of talk about spectrum, and rightfully so, over the last couple of days. So we have a couple of different options in terms of NTN. You've mentioned the MSS approach. We also have seen sort of the leasing terrestrial spectrum, making those sorts of arrangements. In a lot of cases there, it's low to mid-band spectrum. So what other spectrum bands should people be aware of that are being explored or under consideration? And Joseph, I'm going to start with you on that one.
Thank you for the question. So what I would say is the following. Today, when we think of non-terrestrial networks, yes, we have actually two pools of a spectrum that people are kind of comfortable with. We have the lower bands or mid bands. Then we go to the other extreme and we talk about optical inter-satellite links or even through the atmosphere optics. And again, there are interesting problems involved. At lower frequencies, you have the easier coverage, not easy, but easier than certainly if you go to optics. And as you can imagine, I'm going to say, and what happens in the middle, right? So I'll give some numbers. Today, at sub-terahertz frequencies, between 100 and 300 gigahertz, we have the same power on a chipset as you can have in Wi-Fi or a 5G modem, talking about hundreds of milliwatts of power. But in the same footprint that you may have a 3 or 4 dBi antenna in 2 to 4 gigahertz, I can give you around 30 dBs of gain. In other words, I can focus my power 1,000 times better than it would happen at the lower frequencies. So actually, it's not that bad. Actually, moving to higher frequencies, again, I'm not asking for a few terahertz. I'm asking just 100, 200 gigahertz. It's not that bad. Now you will say, oh, but I thought that the atmosphere is your enemy. It is, but it's even worse at optics. So if we are willing to consider optics, why would you skip the middle? And I think that what happened is that no one had an advocate for the middle. I take that hat, and we're trying to do that. So what we're trying to say is that it's not that new frequencies will come and replace. The contrary, we're trying to add ingredients, and then let's hope that as a team, we can come up with the best recipe.
So in order to get that kind of, and you're still within power emission limits in terms of what could go into a smartphone device?
To some extent, yes.
To some extent, okay.
We're not that much worse than millimeter wave.
Okay.
This way.
That's in a reasonable ballpark that could be tinkered with then.
And just to make sure everyone comfortable, I mean, we're making everyone comfortable. We are studying the side effects of that type of very focused radiation. So that's a conversation for another day.
Okay. But, potential flat panels, where you have a larger device and different power
Yeah.
calculations there. Okay, interesting. Other thoughts on spectrum and what you're keeping your eyes on? Well, obviously, you know, Mark, you and I have talked a little bit about that. Do you want to add any additional thoughts in terms of, you know, obviously higher is on the table in a lot of contexts when it comes to 6G and the terrestrial network?
Yeah, so I do think right now there's a lot of focus on direct-to-device, which really means cell phones, smartwatches. I think that now that people are seeing that that's possible, and they are understanding some of the limitations of those antennas, there is interest in things like vehicles. Can I augment vehicles where a vehicle could have a larger antenna? Okay, and while yeah, I do think there's definitely interest in higher frequencies, seeing both terrestrial and satellite, for instance, being interested in E-band now, which is in the 90 gigahertz range. So we'll get to the hundreds, but I think first we'll get to the high you know, close to 100. But the other thing is there's now interest in extending what are more traditionally satellite broadband bands, millimeter wave bands, so that would be Ka, V-band, onto vehicles. And that, right now, I think there's interest in the standards bodies to how that would be done. But again, I think the standard bodies would like to see that with standard waveforms. And so that, right now, I think what you're seeing on release 17 and 18 is this convergence among the terrestrial and the cellular networks. I think what we need to see would be to see the same types of convergence at these millimeter wave bands in order to get the benefits of 3GPP. And there, the physical transmission characteristics are sufficiently different right now. I think it's going to take some work to get there, but I think it's on the roadmap.
Carmel?
So same. So agree with Mark. I mean, we're always looking, going higher and higher in the like, spectrum is everything, right? It's what we monetize at the end of the day. So we continue to push those limits as we look into different feeder link frequencies. That's you know we've gone Q and V for a number of our future plans, and so we'll continue to push that. I mean, we have to do it. You know, as an operator, we have to do it from a bit of a practical perspective. I mean, so we have R&D projects that go obviously all the way up to optics, which is lots of fun. But we have to be somewhat pragmatic as well in terms of what we implement.
Okay. And Mahmoud, how is Link approaching the spectrum conversation?
Yeah, in terms of spectrum, so I think I mentioned this. We shared with the MNO their spectrum, so we use their spectrum to provide coverage in places without coverage. So our approach is sub-1 gigahertz spectrum, right? So there's better propagation characteristics and a lot of other reasons from a technical perspective. But also it's available everywhere, right? So almost not a single MNO doesn't have sub-1 gigahertz spectrum, with very, very, very few exceptions. But almost all conversations we've had with MNOs confirm that.
Okay. Questions from the audience? Yes. Just go ahead.
Okay. So I'm Amitabh from Nokia, and we have been involved with NTNs for a long time, with ASTs and everything else. And what we think is terrestrial is always the key, right? So we provide NTN where there is no terrestrial coverage, like Wyoming or Yellowstone National Park or wherever. You provide coverage where there is no terrestrial coverage. Having said that, we looked at both regenerative and bent pipe architecture. The issue we have is from a infrastructure player in Nokia is the business case. How many base stations we can sell? For regenerative architecture, we have to weatherize the base station to, so it involves development cost and software cost, all these costs. And to make it commercially viable, we have to sell enough of them. So the question is, have you guys looked into the business case for NTN? Having said that, I know the launch costs have decreased, the number of launches are frequent, so it is more viable now than during the Iridium days when Motorola was the first to do Iridium. So that's the main issue. And the second issue what we have is you'll never provide broadband services, right? It is because the antenna gains, especially on the uplink, is difficult. Although now the antenna gains are in the satellite is huge 400 square meter antennas. So the uplink is a big problem. The other problem is, the main problem is convincing about the business case. The second issue, this is with respect to LEOs and GEOs, and I think global IoT services is a very good use case with even GEOs. The last thing I like to point out, you never talked about HAPS. How can you make HAPS profitable? Because with HAPS, you see the link budget is better, but the problem with HAPS is that there is no standardized vehicle, right? So there is weight, power restriction for each kind of vehicle, and one cannot develop infrastructure for each type of vehicle because it is cost prohibitive. So any comments on HAPS?
So business case, and who wants to start?
So I'll jump in. So from a business case, I mean, we think actually the NTN business case is pretty easy, right? So as I mentioned, taking a standards-based approach, working through 3GPP, looking at the NTN standards, helps us in terms of expanding our supplier infrastructure and our supplier ecosystem. So that's going to help drive down the cost of our services. And it expands our user community, right? So we can look at land mobility customers. And know, in our case, if we're using our GEO satellite fleet, we can't use the smartphone antennas, right? But we can look at connected vehicles, which is, maybe a small form factor ESA antenna, on the roof of a vehicle, agriculture, precision farming. I think there's a lot of use cases out there that are comfortable with those kinds of devices. So for us, the business case is easy. It's much easier for us to take a standards-based approach, look at extending services that the terrestrial network operators are already providing, and it expands our user base.
My question, how many base stations I can sell?
Are you selling satellites?
Yeah.
No, I'm not selling. See, for GEO, there is only very few satellites which can cover the whole Earth, you see. Unless it is the volume. How do we get the volume?
Yeah, I can. Okay. So one is, before when you asked about the MSSA, we are attracting other people from the ecosystem. So Ericsson, you mentioned Ericsson, recently joined. And it's really for the case that you're describing, which is to understand what that business case is. So one thing is, if you look at the O-RAN stack, there's only one part of it that probably is going to be affected by NTN versus a purely terrestrial application. The other is what we think is that if you lay out the issue about the sovereignty that I described and countries' desire to have control of that, put that in a roaming environment, there's likely to be a very large number of gateways. Now, those gateways need to be very inexpensive from a satellite, feeder link interface perspective, which we've done even at broadband. So I think that's workable. There are, I think there's several O-RAN companies that are either have joined or will join. Same thing will be on the chip companies. And the whole focus of this is to drive down airtime costs. But the biggest issue is going to be in space. It's the satellite infrastructure that is the most expensive. Sharing that goes a long way, but also getting very high throughput through the satellites. Turns out that's very much electrical energy in space is expensive, and so putting it all towards radio emissions and not towards onboard processing that you can do on the ground is very helpful in increasing throughput, both uplink and downlink, and in driving down airtime costs. So that's so far the things that people like GSMA and others have resonated with, and what we're doing is everything's focused on driving down airtime costs, which is what we think is going to be the issue in scaling these services.
Okay. Joseph, I thought I saw a little nod over there. So I'm just wondering if there are any technical aspects that sort of dovetail to, you know, the argument for a business case.
So as an academic, usually I don't think too much about business. But having said that, we need that, right? And I understand, I've discussed before, I mean, this type of question with Amitabha. He knows that I advocate for terahertz. He knows that I'm for NTN. And he's always the same, where's your business case? Right? So I agree. I mean, we need that. And I agree that the most expensive part is the infrastructure in space. The good news is that, as we were saying, it's cheaper today than it was 10 years ago, even 5 years ago. Also, we talk about infrastructure that maybe they can answer me better, right? But it's for how long does a satellite last, right? And how often are we going to be renewing that infrastructure? If we come up with the next chipset that gives much higher power efficiency, right? How quickly will it make sense to renew that, right? It's not just about putting them out, it's keeping them and renewing them. So.
And that's a very different calculation in cellular than it has been in satellite.
Yeah.
So Mahmoud, Link is one of a number of companies that is relatively young in this space. So the economics are a different calculation for you folks than for the established satellite players. So what do you see as the business case that, you know, is going to help your company be successful ultimately?
Yeah, so I think the main thing to look at is the device itself, right? So if you're working with existing mobile phones, then the cost of the device to the end user goes down to almost zero, right? And then from a satellite perspective, obviously we're in low Earth orbit, so we not only serve one country or several countries, but we serve the entire globe. So we don't need to make all of our money in one country, but it can be spread in various parts of the world. And in fact, MNOs like that because they can market the service differently in different markets and potentially have even different pricing in different parts of the world as well.
I want to circle back to another point that you made about HAPS. Because I think that has been something that people have been exploring. For those who are unfamiliar, HAPS is sort of, it's a bit of a midpoint between low Earth orbit and terrestrial. So stratospheric drones, you know, they're balloons or you know, the large wing flying have gone up as well. I think SoftBank has a lot of that IP at this point. Any thoughts on the potential role there? Because that's also non-terrestrial. That is also something that is being considered as part of the standards. I don't think anybody's made it work commercially. Google tried with a loon. They ended up wrapping that. But we do see, you know, people still dabbling. Dabbling got the smile, so.
Yeah, so for us, I mean, it turns out if you look at like one of the dominant issues for terrestrial telecom is a measure, you know, it's called either, you know, like in fixed services it would be capital investment per home passed, or on the mobile side it would be, you know, capital investment per potential subscriber. The big issue is if you do a satellite system, your costs are higher, but the homes passed or subscribers passed is so much greater that the cost per home passed or subscriber passed is generally better at higher altitude. And with, you know, if you look at these non-geosynchronous satellites, it actually is probably a better trade-off. As you get closer to the ground, the homes passed or subscribers passed gets smaller and smaller really fast. And that tends to be the trade-off, is making that work.
Yeah, that's what we always say too, is that for a LEO system, for example, if you want to add capacity over Cleveland, which is a major airport hub, you're also adding capacity in the South Pacific where there's no subscribers. But from HAPS, so we've been quite interested in it for several years, and you know, it feels like there's maybe a sweet spot in terms of subscriber density where it's not super rural, but basically a low density. But you have to have the right vehicle, so it's a cost cost coverage trade-off. And we did some experimentation in it a few years ago. I've partnered with DT on some experiments. So I'd say, you know, it's still nascent. I think the business case is the problem, and then just finding. You know, there's operational challenges, right? Launching and landing, you know, the orbits for these HAPS devices very small, and so there's this continual launch and land over your service area. And that's a new capability. It's certainly not something a satellite operator is used to doing. So it's interesting for us. I think it's something we're going to continue to monitor and see if we can get the right balance of equation. It's not a global solution, but kind of another gap filler.
I thought I saw another question over here.
Good morning. Great panel session. Loved it. Worked on Iridium almost 3 decades ago, so kind of firsthand know all the problems you guys talking about. Was parts of the HAPS team when I was working at Nokia, so well know that area as well. But what got me curious, Mark, was your comment about the work that's being done in 3GPP. You specifically mentioned a couple of releases. And I'd like to get your view on how do you think will 3GPP approach the air interface when it comes to terrestrial and non-terrestrial networks? Thank you.
So we're working on it. There are a few details. I think actually, I mean they're pretty esoteric. They're things like what should the physical layer waveform be in satellite, because power is so precious. You'd really like to have a constant envelope solution as opposed to non-constant envelope solution. That'd be an example of one of the things that might be an issue. It's not a deal breaker. I think from a satellite, from an NTN perspective, we can deal with those issues. I think the other ones will be around standardization, especially because in the satellite space, physical layer waveforms tend to be tied to different operators and satellite designs. So there's going to be some horse trading and jockeying, I think, on the physical layer stuff. The other thing I do want to point out, though, and this goes to the HAPS thing and the satellite, is the power flux densities that you can get, where it used to be that might be, you might be able to deliver higher power flux densities by being closer to the ground. Now you can pretty much make whatever the regulatory limit's going to be from an interference perspective from any altitude. So that's going to take away some of the benefits of being lower, but you still are going to have total power issues, no matter what the platform is, and that's going to have all those things going to go into the horse trading on the physical layer waveforms.
Any other thoughts on physical layer?
I mean, what I can quickly say is that we still don't know what's the best physical layer, right, at any frequency. And I think that there might be more than one, and that connects a little bit to the idea that, again, we're creating ingredients. We maybe don't know yet the best recipe. And just to add the word that has not been said today, maybe AI can help with that. So I'll finish with that.
How'd we get through the panel without saying
know,
AI till
right?
now?
Yeah,
It's
exactly.
That was one of my questions. That was the next one I was going to ask. I wish we had time to get more, but we need to wrap up right now. So I'm going to thank all of you so much for this great conversation. Thank you so much for contributing, and thank you, Alex, again for having us.